Welcome you all for this course on Geotechnical Engineering I, for which the prerequisites are Engineering Geology and Engineering Mechanics. In this session, we are going to look at first unit, which is Physical Properties of Soil. But before we get into the first unit, let us have a look at some of the interesting and important applications of geotechnical engineering. You probably are aware that one of the important applications of geotechnical engineering is the design and construction of safe and economical foundation for structures which are referred as the earth supported structures in the form of buildings, bridges, machines and transmission towers, etc. If the foundations are having a depth which is less than or equal to the width of the foundation is referred as the shallow foundation. These are the different type of shallow foundations, and this is the raft foundation, which is also a type of shallow foundation. These are the foundations for machines in the form of block foundation, box or caisson foundation and wall type foundation. All these form the shallow foundations. But where the depth of foundation is greater than the width of the foundation is referred as the deep foundation. Example are the most commonly used pile foundations for heavy and tall structures, the legs of the transmission towers, and deep foundations in the form of either pile foundations or the well foundations. They are provided commonly for the abutment and piers of the bridges. Now, apart from earth supported structures, there are other applications of geotechnical engineering, that is the design of proper selection of suitable material for structures which are constructed using soil as construction material, which are referred as earth structures in the form of earth dams, embankments and canal banks. So you can see the earth dams constructed or shown over here, embankments of highways and railways. So this is an embankment of railway. These are the canal banks. So in these earth structures, the role of geotechnical engineering will be the selection of suitable material for the construction of these earth structures and also quality control during construction. The third and important application of geotechnical engineering is the design of the retaining walls and other type of structures, retaining structures, which are referred as earth supporting structure, where the soil needs to be given some support. Okay, example of the retaining walls, sheet piles and coffer dams, and these are referred as the earth supporting structures. So you can see here a highway. To facilitate the construction of a highway in a hilly area, the adjoining hill slope needs to be given adequate lateral support, which is referred as the earth supporting structure. Similarly, in a hilly terrain, when building is constructed, the foundation soil needs to be given lateral support because the natural ground level may be at a lower level. And these are the coffer dams which are constructed in port areas. Now, another important application of geotechnical engineering is whenever you want to ensure safe and economical design of foundation for a structure, what are the causes of failure of such structures? So it is to be investigated. So a brief outline of the causes of failure from geotechnical engineering point of view has been shown over here. Generally, failure occurs when the critical stress in soil exceeds the ultimate strength. So, this is the fundamental cause of failure. But there is another cause where there are some maximum permissible settlements to ensure stability and long-term safety of the structure. When these settlements are exceeded by the actual settlement of the soil, underlying soil, okay, so then this also will cause failure of the structure. So, example is the soft clay, where the soil is highly compressible, leads to very huge settlements spread over a very long time. Similarly, if you look at black cotton soil, okay, the change of seasons, say during rainy season, the soil absorbs water and undergoes increase in volume of the soil manifold. Similarly, during dry season, say summer, the water is evaporated and the soil again undergoes shrinkage. So this causes upward and downward movement of the structure may not be perceptible to the eye, but still the movement of the soil in upward direction, downward direction, it is sufficient to cause distress to the foundations, plinth, floors and walls of the building. Okay. Similarly, in the case of loose saturated sands also, suddenly applied loads such as earthquakes may cause increase of pore water pressure, leading to sudden decrease in the effective stress, turning the soil into a liquid. The phenomenon is called the liquefaction. Okay? So these are some of the important causes of failure of the soil. Failure of soil due to excessive settlements in soft clay is shown over here. Similarly, differential settlement of different parts of the structure may also cause some failure. The classic example of the Leaning Tower of Pisa, constructed in 1370 AD, which is 183 feet tall. Okay? So this is a classic example of differential settlement. Interestingly, a tower of a temple of Sri Brihadiswara temple, which is taller than the Leaning Tower of Pisa, that is 216 feet, constructed 360 years earlier to the Leaning Tower. It is standing erect without any settlement problems. It is very interesting to the engineering marvel of the construction those times. So you can see that when the highways lose the support of the soil, okay, it leads to their catastrophic failure. And the phenomenon of liquefaction I was referring, when suddenly applied loads, for example, the Taiwan earthquake and the Japan earthquake in 1964, where the structure seems more or less intact, but it lost the support of the soil because the soil has been turned into more or less a liquid due to the effective stress reducing to almost zero or negligible value, leading to loss of shear strength, especially in loose saturated sands. So these are the causes of failures, and if we look at the course outcomes of this particular course, Geotechnical Engineering I, we are in the first unit. So for the first unit, the applications of the course outcome for the first unit are applying principles of soil mechanics to estimate the physical properties of soil, and the other course outcomes will be referring when we deal with the respective units. This is the syllabus for the GT1, and different units are there, 1 to 5 units, and different chapters are there. We are currently in the physical properties of the soil, first chapter and first unit. And this is the CO-PO mapping. This is the course outcome CO 1 to 5, and which is correlated with the program outcomes and the program specific outcomes, okay, to the level of slight, moderate and substantial, indicated with the numbers 1, 2 and 3. And so these are the program outcomes as defined by Washington Accord. The first 5 program outcomes are the domain specific outcomes in the form of engineering knowledge, problem analysis, design or development of solutions, and conducting investigation of complex problems and use of modern tools. The remaining 7 program outcomes deal with they are more or less referred as the professional outcomes. They are common for across the domains, and they are actually engineer and society, environment and sustainability, ethics, individual and teamwork, communication, project management and finance, and lifelong learning. And apart from program outcomes, there are also program specific outcomes, and specifically this subject of Geotechnical Engineering I, it correlates to program specific second PSO, that is analyzing and solving stability problems in soils for design of foundations, earth structures. So this part will be, the course outcomes will cater to this part of second PSO. Okay. So coming to the textbooks and references for this particular subject, the first classical textbook written by father of soil mechanics, Dr. Karl Terzaghi. Okay, the book was written in German, titled as Erdbaumechanik, meaning soil mechanics, published in 1925. And there are other books which have come up from Terzaghi and Terzaghi, Peck and Misri, titled Theoretical Soil Mechanics in Engineering Practice. Okay. There are many other important textbooks, and there is this particular textbook I am referring. This is authored by Dr. B.N.D.Narasinga, that is myself, as Soil Mechanics and Foundation Engineering. It is published by Wiley and published in 2015. So there are numerous references for this course of Geotechnical Engineering in the form of NPTEL courses offered by different IITs. Now coming to the first unit, we are dealing with the physical properties of soil, and you have different type of soils, like gravels, which are more or less coarse, larger in size. Lesser in size are the sand compared to gravel, and then particles having lesser size than gravel and sand are referred as silt, and clays are those having particle size usually much smaller than gravel, sand and silt, and also having certain minerals called clay minerals. So these are the different type of soils, and if you look at the type of soils, you can see that what you find is you have solid particles, and between the solid particles in the form of groups of particles, you also have void space between the groups of particles. So this comes to referring to the soil as the three-phase system. Okay, so the three-phase system of soil consists of, if you take any given mass of soil, it consists of solid particles, individual solid particles or group of soil particles. Between the solid particles there is void space, and this void space is occupied by either water, which is referred as the pore water also, and the air. Okay, so when you actually calculate the volume, when you put the mass of solid particles together, you have this three-phase diagram in the form of mass of solid, mass of water and mass of air. Okay, so this forms the three-phase diagram, which is very, very important and fundamental in understanding the physical properties of soil. So this is the schematic diagram which represents the three-phase diagram consisting of the solids, soil solids, water and air. So you can see that on the right hand side of the three-phase diagram, the volumes are represented. So a given volume of soil consists of volume of voids which may be occupied by water, air or both, and the solid particles, therefore volume of solids. The volume of voids again consists of volume of air and volume of water. Similarly, on the left hand side of the three-phase diagram, the weights are represented. Okay, so therefore, W, capital W is the weight of the entire mass of soil, and this weight consists of the weight of the solid particles, which is also equivalent to the weight of dry soil WD, and the weight of water WW, and the weight of air WA, which is normally taken equivalent to 0 because it is negligible. So therefore, you can see here that the weight of solid particles is equal to the weight of dry soil. The total weight of soil is equal to WD plus WW plus WA. When WA is considered negligible, W is equal to WD plus WW. Similarly, if you consider the volumes, the total volume of soil is the sum of volume of solids and volume of voids, and the volume of voids is the sum of volume of water and volume of air. Therefore, if you substitute for VV equal to VW plus VA, then the total volume is equal to VS plus VW plus VA. Okay. So therefore, this is three-phase diagram forms very fundamental, important thing to remember and understand. Okay, to understand the physical properties of soil and the interrelationships between the physical properties. So you can see during dry season, the void space between the solid particles consists of only air because water is completely evaporated. Similarly, a mass of wet soil, if you place it in the oven for sufficient time, the water is evaporated and the void space entirely consists of only air. So this is the dry soil where the void space contains only air and it does not contain water. Therefore, volume of voids is equal to volume of air for a dry soil, and the weight has only two components, weight of air and weight of dry soil or weight of solid particles, WS or WD, and weight of air anyway is considered negligible. Okay, so this is if you see here, earlier we have referred to the three-phase system of soil and a three-phase diagram. This is a case of two-phase diagram consisting of only air, the gaseous phase, and solid particles, the solid phase. On the contrary, if you see in a rainy season, the upper layers of soil near the ground surface, the void space may be completely filled with water. Okay, and therefore no air may be present in the void space, and therefore this is again a two-phase system of soil, and the two-phase diagram consists of water and solid particles. So here the volume of water is equal to the volume of voids. Okay, and you have the total weight is equal to here weight of water and weight of dry soil, their sum. So these two are the extreme cases of the three-phase diagram of soil. When the water content is 0, you have the dry soil with a two-phase system and two-phase diagram. When the entire void space is completely filled with water, you have again a two-phase system consisting of only water and solid particles. Somewhere between these two extreme conditions lies the three-phase system, which is a partially saturated soil where the void space may be partly occupied by water and also air. Okay, so here the soil is referred as I mentioned earlier, the three-phase system consisting of solid phase, the solid particles, liquid phase, the water, and the gaseous phase, the air. So this is the partially saturated soil, and the diagram is referred as the three-phase diagram, which is somewhere intermediate between the dry soil and the fully saturated soil. Now, let's start with the physical properties of soil. There are different sets of physical properties. First set of physical properties are defined in terms of the ratio of volumes of quantities. So, the physical properties which are defined in terms of the ratio of volumes are, there are 5 such physical properties: void ratio, porosity, degree of saturation, air content, and percentage air voids. There is only one physical property which is defined in terms of the ratio of weight of the materials, that is water content. And there are again 5 more physical properties which are defined in terms of the ratio of weight and volume. Obviously, it is unit weight, bulk density or unit weight. Okay, so bulk unit weight or bulk density gamma, dry density, saturated density, submerged density or submerged unit weight, and density of soil solids or unit weight of soil solids. And the fourth variety of physical properties are the specific gravities, okay, which are defined in terms of the ratio of density of a material to the density of water. Okay, so you already read it in physics in your schooling and in +2. So there are 3 types of physical properties which are defined in terms of the ratio of densities: specific gravity of soil solids, absolute specific gravity, and mass specific gravity. So let us try to understand each of these physical properties. The first one is, there are 5 physical properties which are defined in terms of the ratio of the volumes. So first one is the void ratio. The symbol is E, okay, which is defined as the ratio of volume of voids, okay, to the volume of solids. So, okay, E equal to VV by Vs. Okay, so because it is a ratio of volumes, it has no units. Okay, the units in the numerator and denominator get cancelled. And void ratio is a very important property which affects the permeability and compressibility. The higher the void ratio, higher will be the permeability and higher will be the compressibility in general. Okay. Similarly, the density and shear strength, okay, they are also significantly affected by void ratio. Lesser the void ratio, then more will be the density and more will be the shear strength in general. Generally, void ratio is determined indirectly, okay, using some of the relations like GW equal to SE, which we will see in the latter part of this session. And the void ratio E is also given by this equation, E equal to G gamma W by gamma D minus 1. And the usual values are, void ratio of a soil can take any value greater than 0. Okay, it's not that void ratio is to be less than or equal to 1, not necessary. Void ratio in some soils, clayey soils especially, can have values greater than 1 also. Okay. Now the second physical property defined in terms of the ratio of volumes is porosity. Okay. The symbol is N, okay, and N is defined as the ratio of volume of voids to total volume. Okay. So previously void ratio was defined as the ratio of volume of voids to the volume of solids, whereas here in porosity, the same volume of voids is defined in terms of the total volume. Okay, so N is VV by V. So, like void ratio, porosity also has no units, and generally, because the denominator is more for porosity, the value of porosity is less for the same soil compared to the void ratio. Okay. Porosity is more used in geology, and void ratio is a term more used in geotechnical engineering. So usual values, if you can see, okay, definitely void ratio, porosity cannot be 0, okay, because in any soil there will be certain amount of void space available. Therefore, void ratio, porosity cannot be 0, it is always greater than 0, and the void space cannot be, equal to the total volume. Okay, so therefore, the value applicable range of porosity are greater than 0 and less than 1. Third one is the degree of saturation, defined as the ratio of volume of water to volume of voids. The symbol is S. Some books refer degree of saturation by the symbol SR, S suffix R. Okay, and there are no units. Applicable values are degree of saturation greater than or equal to 0 and less than or equal to 1. Okay. And air content, if you refer degree of saturation, the denominator is volume of voids, and the same denominator is used in defining air content, which is the volume of voids. In degree of saturation, volume of water is used. Here the volume of air is used, because the volume of voids consists of air and water. If you are considering volume of water versus volume of voids, it is a degree of saturation. If you are considering volume of air versus volume of voids, it is air content. Okay, so air content, A suffix C, is defined as the ratio of volume of air to the volume of voids. Okay, so there are no units. The applicable values, it can have any value greater than or equal to 0 and less than or equal to 1. And if you compare, okay, as I mentioned, the denominator is same for both. Okay, and where for soil, for a dry soil, there is no water and degree of saturation will be 0 there, and air content will be equal to 1. Okay. For a fully saturated soil, the entire void space is occupied by water, and therefore air content will be 0 and degree of saturation will be 1. So obviously the sum of S and AC, degree of saturation and air content, is equal to 1. Okay, because the denominator is same, and in the numerator we are referring to the two components of the volume of voids. Now coming to the percentage air voids, okay, it is defined as the ratio of volume of air to the total volume. Okay, the symbol is Na, so Na is Va by V. Okay, note that all volumes are represented by capital V. Okay, there are no units. The applicable values are Na is greater than 0. Generally, percentage air voids is referred in the units of percentage, and Na is less than 1 always. So what is the practical use of percentage air voids? Generally, if you consider compaction, okay, you will see in unit 5 of this course, compaction, where the effectiveness of compaction is referred as the removal of or expulsion of air from the soil by some mechanical means such as rollers. So the effectiveness of compaction can be determined by compaction is considered most effective when percentage air voids is equal to 0. That's why there is a relationship between the dry density and percentage air voids as gamma D equal to 1 minus Na G gamma W by 1 plus GW. Now summarizing the physical properties in terms of the ratio of volumes, you have void ratio and porosity whose numerator is same, volume of voids, whose denominator is Vs and V. Void ratio, the denominator is volume of solids, porosity the denominator is total volume. The volume of voids are being expressed in the form of, in terms of the ratio of the volume of solids, it is void ratio. In terms of total volume, it is porosity. Similarly, if you compare degree of saturation, okay, the denominator is volume of water, and which is also the denominator for air content, okay. And the percentage air voids, if you consider for both air content and percentage air voids, the numerator is same, volume of air, okay. And the next physical property, there is only one physical property, very important, which is defined in terms of the ratio of weights of quantities, that is water content, also called as moisture content, okay, right. Now the symbol is W, small w, okay. Capital W is used in geotechnical engineering for weights, okay. Therefore, small w should be carefully used to represent water content. So W is weight of water by weight of dry soil, as usually expressed as a percentage, okay. So the weight of water divided by weight of the dry soil or weight of solid particles is referred as the water content, okay. So because it is a ratio of weights, it has no units but expressed usually in terms of percentage. And the applicable values, yes, water content can be 0 when the soil is dry, and it can have even value greater than 1 also, or greater than 100%. There are soils, typical clay soils, where the weight of water can be greater than the weight of dry soil. You can have water contents only occasionally in the case of some of the clayey soils, okay. So the natural water content is the water content of an in situ soil at any time, okay, during any season, okay. It varies from season to season. Similarly, water content is very, very important. Consistency limits or Atterberg limits are expressed in terms of water content, and optimum moisture content used in compaction, it is also expressed in terms of water content. So water content is commonly one of the common steps in many of the experiments conducted in the laboratory related to geotechnical engineering, okay. So there are 5 unit weights which are referred as the ratio of weight and volume. So bulk unit weight or bulk density, the symbol is gamma, and bulk unit weight is defined as the ratio of total weight to the total volume, okay. And the next type of unit weight is the dry unit weight, gamma D, the symbol is gamma D. It is referred as the weight of dry soil to the total volume of soil. So gamma D is WD by V, okay. And the saturated unit weight, when the entire volume of voids is occupied by water, then the unit weight of soil is referred as the saturated unit weight. Weight of it is the ratio of weight of saturated soil to the volume of soil, and it is referred by the symbol gamma sat. And submerged unit weight is either gamma dash or gamma sub. It is the ratio of weight of submerged soil considering based on Archimedes principle. Whenever an object is immersed in liquid, it appears to lose some weight. If you consider the weight of submerged soil, weight of soil in dry submerged condition, it may be somewhat less than the weight of soil in the saturated condition. Divided by the total volume refers to the submerged unit weight. And there is also important unit weight for the solid particles, which is the unit weight of soil solids, gamma S. So gamma S is obtained by dividing the volume of solid particles, okay. That is, the weight of solid particles divided by the volume of solid particles is referred as the unit weight of soil solids, gamma S, okay. So the units for all the unit weights are, as you know, the ratio of weight and volume Therefore, it is kilonewton per meter cube in SI system. And if you refer MK system, it may be gram force per cm cube. Okay, cm cube means cubic centimeter. It is also referred as cc. So gram force per cc. Okay, so this is the unit for unit weights. Now let's see how the submerged unit weight can be determined. Okay, what is the expression for submerged unit weight? We know the Archimedes principle, where when an object is immersed in liquid, it appears to lose some weight. This loss of weight is equal to the weight of the liquid displaced by the object. Now, when a soil mass is completely saturated, a liquid whose volume is equal to the total volume of the soil is replaced by the soil which is in the submerged condition. Therefore, as per Archimedes principle, the submerged weight of the soil is equal to the weight of saturated soil minus the volume of the liquid which is being displaced by the soil, that is V, into the density unit weight of the water. So therefore, W sat minus V gamma W is the. So if you see this, gamma dash will be then equal to W weight of submerged soil divided by total volume, which we have written this expression, and therefore if you separate the terms, it will be W sat by V minus V into gamma W by V. So here V and V will get cancelled, and W sat by V is nothing but gamma sat, the saturated unit weight. So and gamma W by V is nothing but the unit weight of it's just gamma W. So therefore, the submerged unit weight of soil gamma dash is nothing but the difference between the saturated unit weight and the unit weight of water. Okay, so it's important, of course, to know that the unit weight of water is 9.81 kilonewton per meter cube. Now coming to the last set of physical properties, which are the specific gravities. Okay, in physics you have read them as relative density, but relative density is a term which is reserved for some other physical property in geotechnical engineering. Here, specific gravity, all specific gravities are in terms of the ratio of unit weight of material to the unit weight of water. Now, the specific gravity of soil solids, which is the first type of specific gravity we are defining, the symbol is G, and it is defined as the unit weight of soil solids, gamma S, ratio of unit weight of soil solids to the unit weight of water, G equal to gamma S by gamma W. So we know that gamma S unit weight of soil solids is Ws by Vs. Therefore, G will be equal to Ws by Vs gamma W. Ws is nothing but the weight of soil solids, which is also equivalent to weight of dry soil. Therefore, you can write this G as Wd by Vs gamma W also. Okay. So because it is the ratio of densities, specific gravity has no units. Okay, and the specific gravity of soil solids may also be just simply referred as the specific gravity of soil. Although there are different types of specific gravity, without any qualifying word, if the word specific gravity is used, it refers only to the specific gravity of soil solids. Okay, there are important applications of specific gravity of soil solids. Okay, okay. Specific gravity is also referred as the absolute specific gravity or true specific gravity. Okay, there is also absolute or true specific gravity. If you exclude the void part, okay, there are some impermeable void space within the crystal structure of the solid particles. If you exclude them, then what you get is the absolute or true specific gravity, which is different from the specific gravity of soil solids. And absolute specific gravity or true specific gravity is used for research applications. The second type of specific gravity is the mass specific gravity, also referred as the bulk specific gravity, which is the ratio of bulk density or total density to the density of water, or the total unit weight of soil to the unit weight of water. Gm equal to gamma by gamma W. So we know gamma is total weight of soil divided by total volume of soil. Therefore, Gm is nothing but W by V gamma W. Okay. So mass specific is also called bulk specific because we are using the bulk density in the denominator in its definition. And another name for mass specific is apparent specific gravity. Okay. So there are no units for mass specific gravity. So applications of mass specific gravity are there specifically in shrinkage limit calculations. We will be seeing its use. So we have referred it earlier. Unit weight of water is very important. Okay. It is in MK system, the unit weight of water gamma W is 1000 kg F per meter cube, or it is 1 gram force per cm cube. Okay. Also referred as 1 gram force per cc. In SA system, the gamma W value is equal to 9.81 kilonewton per meter cube, or 9810 newtons per meter cube. So let's summarize our discussion on definitions of physical properties of soils. So void ratio and porosity, void ratio E and porosity N have been defined. You can find that the numerator is same in both volume of voids, and the in void ratio, volume of voids is expressed as a proportion of volume of solids, and in porosity, volume of voids is expressed as a proportion of total volume. And degree of saturation and air content, if you observe S and AC, the denominator is same. So in degree of saturation, volume of water is expressed as a proportion of the volume of voids, and in air content, volume of air is expressed as a proportion of volume of voids. So denominator is same, and the sum of degree of saturation S and air content AC, it is equal to 1. Percentage air voids and air content, if you observe, so in both air content and percentage air voids, the numerator, it is same. Volume of air is being expressed here as a proportion of volume of voids in the case of air content and total volume in the case of percentage air voids. So obviously in percentage air voids, the denominator is more, and therefore percentage air voids is always less than air content because the numerator is same in both the parameters. Water content is the single physical property expressed in terms of the ratio of the weight of parameters. So water content is defined as the ratio of weight of water to weight of dry soil, usually expressed as a percentage. And you have bulk density and dry density. So bulk density is actually a general term, which is the ratio of weight of total weight of soil to the total volume of soil. And dry density is when the soil is in dry condition, the dry density is expressed as the ratio of the weight of dry soil to the volume of soil. So bulk density is a general term when the soil is in any condition, and when the soil is in a dry condition, the bulk density itself will become dry density. Similarly, when the soil is in a fully saturated condition, the bulk density will become the saturated density because the denominator is same and the numerator is becoming the total weight of soil is becoming, because the soil is in fully saturated condition, it is the weight of saturated soil. And as we have seen, the submerged unit weight is the difference between saturated unit weight and the density of water. And this is another important physical property, unit weight of soil solids, which is the ratio of only the solid particles are considered in both numerator and denominator. So So, unit weight of soil solids is defined as the ratio of weight of solid particles to the volume of solid particles. And you have the specific gravity of soil solids, which is the ratio of unit weight of solid particles, soil solids, and unit weight of water. Okay. That is also, of course, equivalent to Ws by Vs gamma W, G equal to gamma S by gamma W, that is equal to Ws by Vs gamma W, or you may call it as G equal to Wd by Vs gamma W, because the dry weight is also equivalent to weight of solid particles. And you have the mass specific gravity of soil as the ratio of the bulk unit weight. Okay.